Hey guys, so this video is going to be about heat and chemical reactions. It's basically stoichiometry with a heat element added. First, let's talk about heat and what that means. So heat can be exothermic or endothermic in a chemical reaction. So an exothermic is all on this side of the screen, and when it's exothermic, the delta H, which is really called enthalpy, okay, but we can look at it as heat for now. We will talk about that more when we talk about thermodynamics. Heat is negative when it's exothermic, so heat is leaving, and heat can be written into reaction as a product. So here, if this is the reaction that's happening, right, we have our reactants over here, which are right here, A plus BC as reactants, and then AB plus C are products. And so you can see if you just look at where you start, because this is energy here, where you start and where you finish, you have lost heat, right? It went down. So since the heat goes down, that means that it was lost in the chemical reaction, and we can actually write our heat. So if this is our reaction, A plus BC goes to AB plus C, we could write delta H because it was lost in the reaction, so that means it's a product. So this value here, if we were to write it, would be a negative number. It would be less than 0. Okay, so in an endothermic reaction, which is all over here on the other side, right, endothermic reactions gain heat. So if we look down here at this reaction profile, if these are the reactants, so this reaction is x squared plus 2y goes to 2xy, then the reactants have this low energy here, and the products have a much higher energy. So that means that this reaction has gained heat, all right? You don't have to worry about this hump right now. That's the energy of activation. We'll talk about that in just a couple of units. All right, so right here it says endothermic reactions gain heat. So the delta H is a positive value. Heat is positive. Heat can be written into reaction as a reactant because it has to be used up. All right, so if I was to rewrite this reaction and include the heat value, I would put it as a reactant, not a product. All right. Okay, so exothermic, heat is lost, it's negative, and it's a product. Endothermic, it's gained, it's positive, and it's a reactant. For each of the following, determine if the reaction is exothermic or endothermic in the forward direction. Rewrite the reaction to include the heat value and answer the question. All right, so before we answer the question, I'm going to do what it says first to do. All right, so since this is positive, right, that means that it's endothermic. And so if we rewrite this reaction, it's going to be N2 plus O2 goes to 2NO, and this heat is going to be a reactant. So there's my reaction, 180 kilojoules plus N2 plus O2 goes to 2NO. All right, so now I can find this value. So I have 13.7 grams of nitrogen, so I'm going to write that down first. And I want to know how much heat will be absorbed. So just like in a chemical reaction, when I use a mole to mole ratio, right, heat is a mole to mole ratio as well. So what I'm going to do here is, I know I don't have a relationship between grams of nitrogen and heat. I have a relationship between moles of nitrogen and heat, because 1 mole of nitrogen reacts with 180 kilojoules of heat. So I need to get nitrogen into moles. And the way that you get nitrogen into moles is you use molar mass. So the molar mass for N2 is 28.02 grams per every single mole of N2. And then the relationship is one of these, right, makes 180 kilojoules of heat. So 1 mole of N2 is 180 kilojoules. So the answer to that is going to be 88.0. And then next it says, what mass of iron must react to produce 3,600 kilojoules of energy? So I'm going to rewrite the reaction. And first I notice that this is negative, so that means it's exothermic. The heat is leaving. And then I'm going to rewrite the reaction. I have 3Fe plus 2O2 goes to Fe3O4 plus 1,120 kilojoules. Right? So this, it means that it's exothermic, heat is leaving, it's on the product side. So if you were to rewrite it in this form, you'd have to remember to put the negative sign there because this is a product, so that means it's leaving the system. All right, so I'm going to start with 3,600 kilojoules. And then I know that the relationship is going to be 1,120 kilojoules of heat, right, for every mole of iron. For every 3 moles of iron. And then I want to get to mass. So when I have moles, so 1 mole of Fe is 55.85 grams, just the molar mass. And so the grams that would be required to produce that much energy is 538.5. And so that rounds to 540 for significant figures. All right, and then the last one is also going to be exothermic. We're going to write out the reaction. 2H2 plus O2 goes to 2H2O plus 571.6 kilojoules, right? All right, so we have 2 values given to us. We have 12 grams of hydrogen, and then we have 76 grams of oxygen. So what kind of problem is this? Do you remember what it's called? It's called a limiting reactant problem, because one of those is going to run out first. So it's just like if you're making a bunch of sandwiches, right, and you have 5 pieces of turkey, 3 pieces of cheese, and 4 slices of bread, you can only make 2 sandwiches because you've only got enough bread for 2 sandwiches. You have plenty of cheese, you have plenty of turkey, unless you like 5 slices on each sandwich. That's besides the point. Whichever one runs out first, that's the most you can make. So if I have 12.0 grams of hydrogen and I want to go to heat, then I have to use a mole-to-mole ratio from hydrogen to heat. So I'm going to use the molar mass. And then for every 2 moles of hydrogen gives us 571.6 kilojoules of heat. And then I'm going to use 76 grams of oxygen and do the same thing. So I'm going to start with the molar mass of oxygen and then use the mole-to-mole ratio, 1 mole of oxygen for every 571.6 kilojoules of heat. So for the top calculation, that gives me 3,402, and it's going to be negative because that heat is given off. And for the bottom one, it's going to be negative 1357.5. So that means that oxygen is my limiting reactant, and that is the amount of heat that is going to be released. Okay, so this heat is let off by the reaction, and after we've released that much heat, there's no more oxygen to react. All the oxygen has been used up in the reaction, so it can't go any further, right? This is all gone. So if this is gone out of the reaction, we can't make any more water, which means we can't produce any more heat. So it can't go any further. It can't make this ever, unless we add more oxygen to the reaction. All right, we got one more. It says if 10 grams of sucrose is burned, the should be a comma there, 165.1 kilojoules of heat is released. Find the heat of the reaction with the appropriate sign and write the reaction with the heat on the correct side of the reaction. It says 10 grams of sucrose, so I know in this reaction that there's only 1 mole of sucrose. Right? So I'm going to turn this into moles of sucrose. So I've got 10 grams. And the molar mass is 342.296. So that comes out to be 0.0292145. In the problem, we said that 10 grams gives us 165.1 kilojoules of heat. And it's released, right? So 10 grams is this many moles down here. So that means that if we look at it, negative 165.1 kilojoules, and we divide it by 0.0292145 moles, then I get negative 51 kilojoules per mole of sucrose. So this is that. If we had had 2 of these, then this wouldn't be correct. It would have to be for 2 moles of sucrose. But since there's only 1, it works for 1 mole.